Kia ora koutou. Today I'm going to discuss the application of 3D point densities to archaeological data as a way to assess formation. This research has been done in collaboration with my colleagues Rebecca Phillipps, Sina Masoud-Ansari, and Simon Holdaway. Artifact location has always been collected in archaeological research. As the old adage has gone, context is key, and archaeologists have long sought to understand the relationships between objects and features. Over the past few decades, the accuracy to which the location of artifacts are recorded has increased in resolution with the advent of new technologies, and likewise, what artifacts are recorded has shifted over time, moving from recording what were once considered important finds or those of typological interest to the recording of all objects that are encountered. Interpretations are usually done through the relation to stratigraphical units, and is usually done in an effort to locate surfaces that can be attributed to discrete time periods or events, or even activities. Density analysis is usually employed in these cases to determine areas of more or less artifactual material, and in some cases is used to suggest potential functions for particular areas of a site. In such cases, density analyses are conducted in two dimensions, with their z-axis ignored and instead considered as part of the stratigraphic unit that they are assigned to. They are essentially binned into these units. However, determining deposits is difficult and they often represent formational processes that are more complex than what is realized in the field, leading to misinterpretations of the relationships of objects in the archaeological record. In addition, deposit boundaries are often unclear, and assigning an object to the top of one layer or to the bottom of a previous one is a conundrum which is often solved subjectively. An alternative approach to 2D density analyses and their attribution to stratigraphic units is to examine the relationships between artifacts to see what they can tell us about the distribution of artifacts and their formation. Here we have taken such an approach to the Middle Holocene deposit of Kom W in the Fayum, Egypt. Kom W was excavated by Gertrude Caton-Thompson and Eleanor Gardner during their 1925 to 1926 field season. On the excavation, they revealed pits, hearth features, faunal material, stone artifacts, and pottery, among other forms of material culture. Based on the identification of these materials, they interpreted Kom W as the remains of a Neolithic village, and this interpretation persisted in early syntheses of the prehistory of the wider region. For example, in Child's Neolithic package and revolution theories. The site was excavated in an unusual way in 20 parallel strips, with the material from each strip used to backfill the previous one. Section drawings of each spit were published and hold data about the pre-excavation surface of the site, as well as the extent of the midden deposits. However, in their printed form, interpreting these data is difficult. In addition, excavation of Kom W has destroyed the pre-excavation surface record, and subsequent looting activities further disturbed it, as you can see on the top image here. Despite the disturbance to the surface of Kom W, we were able to use the section drawings to create a digital model of Kom W that mapped the original surface of the Kom and the extent of the midden deposits in a GIS environment. The model seen on the bottom left is available on Sketchfab. It has also been published in an article in Advances in Archaeological Practice in 2017. By examining the distribution and size of pit features that were uncovered by Caton-Thompson and Gardner on the lowest level of the Kom and the extent of the midden layers we were able to demonstrate that the Kom has been subject to wind erosion over the past 6,000 years from a north-northeastern direction. Also considering extensive surface remains in the surrounding area, which we've labeled the X1 survey area, we demonstrated that Kom W was not a village, but more the most recent deposit in the area, which has been subject to less erosion and therefore has survived. In 2006, two trenches were excavated to the south of Kom W, KW01 and KW02, and this was done to gain a better understanding of the area immediately surrounding the Gertrude Caton-Thompson and Eleanor Gardner excavation, and to what depth the material culture could be found, which was otherwise considered largely clustered near the surface. KW01 was found that 87% of the artifacts were found within 5 centimeters of the surface, and with KW02, 70% of the artifacts were within 5 centimeters of the surface, so largely a surface record. The 3D distribution of the points from these trenches is displayed in front of you, and again it reinforces the notion of a largely surface record. We were able to record these data in such a way because during our work in the Fayum, we took great care to record the 3D positions of artifacts from surface surveys and excavated contexts. For this, we used a total station. The result in a GIS is a large number of points that represent the distribution of artifacts, but are difficult to determine any patterning from. The density of the objects is high, and the stratigraphy is such that determining any pattern based on a 2D kernel density is difficult, and that attributing them to a stratigraphic layers is problematic, as determining what the different layers actually represent is difficult. An alternative approach is to consider the relationship of the artifacts in 3D using 3D point densities. 3D point densities exist as part of the GRASS GIS software suite, but are difficult to use and incorporate with other GIS data. This is mainly because the visual outputs are in a voxel format, which is not currently supported by any GIS interface, and the rendering of which is only possible in specialized renderers or versions of Blender 2.79 and lower. However, thanks to the Blender GIS add-on, we can bring GIS data to Blender, where voxel data can also be rendered, as can be seen by the density cloud seen in front of you. These are the two on the left represent the density of all artifacts from Kom W with a 0.25 meter cubed resolution. A Blender add-on that creates 3D point densities has been created by my co-author Sina, Masoud-Ansari, and myself, and will be available for download on GitHub in the near future. The challenges with the application of this method are many. Having suitable data is foremost, as it requires a rigorous collection method that records all objects in a trench, not necessarily just those that are considered artifactual. In addition, having fine control over the elevation objects is required. And by this, we mean not that just so it exists, but also that care has been taken to make sure the elevations are recorded consistently between days in the field, and even seasons. On one of our other projects on Ahu Great Mercury Island, we have taken great steps to record these elevation discrepancies between days and account for them. Once such data exist and the 3D densities have been constructed, displaying 3D point densities is difficult, as it requires a voxel renderer, as I mentioned. This also presents issues for publishing, as such visualizations are usually limited to 2 dimensions, as the ones I've shown previously, and there is no current efficient means to publish a 3D model with the voxel density, aside from publishing the raw data and having the reader have an independent viewer on their computer. Integrating them with other GIS data is also an issue, but this can be solved by either using Blender GIS or exporting the density values to their respective points for display in GIS programs. It's the latter approach that we've applied to the densities of KW01 and KW02 from Kom W. Here on the top row, we can see the 3D point density values of artifacts from trench KW01 at resolutions of 0.05 meters cubed, 0.10 meters cubed, 0.25 meters cubed, and 0.5 meters cubed. Comparing these to 2-dimensional kernel densities of the matching resolutions, as you can see on the bottom row, there is little or no agreement between them, between the two as to the density of the objects or any respective patterning. On the left, you can see a line graph. This displays the ordered density values from KW01 by resolution. And what you can see is that as the resolution increases, the number of objects with a density value of 0 decreases. These 0 density values represent a form of background signature of formation and likely represent the artifacts that do not contribute to an immediate density pattern, but serve rather to demonstrate where such patterns occur. When the 3D density is considered, what becomes apparent as the dense 3D density increases is that there is a band of artifacts running approximately north-south parallel with the trench, as we can see on the top row. When we look at the density analysis from KW02, a similar issue is apparent, as there is little agreement between the 3D point densities and the 2D kernel densities. However, the linear banding running approximately north-south is also visible in the 3D density, appearing across all the different resolution bands. These are generated because the 3D relationships of the artifacts is considered in respect to their depths, opposed to a 2D analysis pattern, which flattens the z-axis. Tests of artifact size and type offer no clues as to what these linear bands may be. However, when we consider the bands in relationship to the rest of Kom W, they line up in a way that swales would be expected to form from a north-northeasterly wind direction that has been prominent in the area for approximately the past 5,000 years. The distribution of artifacts largely near the surface has been influenced by the movement of aeolian sands over the Kom, the same process which has slowly eroded Kom W to the form it is in today. The dense layer of artifacts on the top of Kom W from the excavation of Caton-Thompson and Gardner were those which they did not collect and have subsequently redeposited on top. These artifacts have somewhat protected the Kom from erosion over the last 100 years since its excavation. However, examination of the artifact densities from the two adjacent trenches show that the deflation of deposits near Kom W has created a similar density pattern, enforcing the interpretation that Kom W has been subject to these processes since the Middle Holocene. Kom W, once interpreted as a Neolithic village, rather represents a place of occupation that was the most recent amongst a wider settlement pattern around the Fayum North Shore. Given another half a millennium of erosion, Kom W would likely exist only as a dense scatter of artifacts, as we have observed elsewhere along the Fayum North Shore. However, through examination of the distribution of artifacts in relation to their 3D distributions, we've been able to determine how these scatters of artifacts are forming. As I mentioned before, we will publish the add-on for Blender, which builds on the existing Blender GIS add-on and allows for the creation and rendering of 3D point densities. It is hoped that the use of this method will introduce a new form of density analysis that will allow for a greater understanding of artifact distributions and what processes might be influencing the distribution of artifacts independent of any stratigraphic deposits which they are interpreted. This method is not to replace stratigraphic recording, but rather to provide a way to consider artifact distributions so that they may serve as an independent line of analysis. If you'd like any more information on our publications from the Fayum project, please visit our ResearchGate project page. We also have a book available through Cotswold Institute of Archaeology Press. And I would like to thank the members of the Fayum project, Professors Willeke Wendrick and Renee Kappers, the Supreme Council of Antiquities Egypt, the Royal Society of New Zealand, National Geographic Society, and the colleagues and students of the affiliated universities. Thank you.